Check. Check. Okay, today's lesson is on resistor combinations. This is the third video of our circuit analysis sequence of videos. So let me give you the problem first. Let's say that we have a voltage source, maybe a 9-volt battery, and it's connected to two resistors. Maybe this one's 1 kilo ohm, and maybe this one is 8 kilo ohms. Okay, and as usual, we want to find the voltage at all the nodes. Maybe our reference node is down here. So this is 9 volts here, but what is the voltage here? And what's the voltage equivalent? We could ask, what's the voltage across this resistor? What's the voltage across this resistor? And we could ask things like, well, what's the current in that loop? Right. Well, so far in this course, you have the following methods of analysis. You have Ohm's law, and now Kirchhoff's law. Kirchhoff's laws. Okay, and you could use Kirchhoff's voltage law to get the current in this loop, but I do want to point out this is a simple circuit, and these two things alone are not going to be enough for us. And I want to point out here that Ohm's law in particular will not work for you on this problem, and that's because it's actually very seldom that we know the current through or the voltage across. And to use V equals IR, you need to know either the current through the resistor or the voltage across. And I want to point out in particular, this is a pitfall that I see from students. You look at this 1 kilo ohm resistor, and yeah, it's connected to a 9-volt source here. And so students are tempted to say, well, the current in this resistor, the 1K, must be 9 volts divided by 1 kilo ohms, 9 amps. That's the current through the resistor I, because there's 9 volts here. Okay? No. Don't do that. That's not correct. And I want to point out again that Ohm's law, as easy as that equation is, it's often misinterpreted. You need the voltage across that resistor. Okay? We have the voltage here relative to this node down here, but we don't know the voltage here relative to this node. We don't know the difference in voltage across there. And so we cannot immediately apply Ohm's law in this circuit. Alright, well, again, I'm assuming you know physics, and let me clean this up a little bit. Okay, I'm going to clean this up a bit. And I think what I had there was a 1 kilo ohm resistor and an 8 kilo ohm resistor. So I'm going to assume you've seen a combination like this before. And in fact, I bet that most people watching this video know that there's an equivalent resistance, call that Req, between these two terminals here, terminal A and terminal B. There's an equivalent resistance, and I bet most, if not everyone watching this video can tell me that that equivalent resistance is 9 kilo ohms. The question that most students get wrong is the following. What does it mean to have an equivalent resistance? Right? We talk about equivalent resistances a lot in physics. Equivalent resistance. right? What does that mean? So if I connect a voltage source, let's say, I connect a voltage source here. Source. And let's make that 9 volts again. And if I connect a voltage source here of 9 volts, okay, we're trying to figure out what does this mean, equivalent resistance. Well, so something is equal in these two circuits. Are the circuits the same? No, they're not the same. This circuit has 3 components. This circuit has 2 components. This circuit has 1, 2, 3 nodes. This circuit has 2 nodes. Okay, clearly these are not the same circuit. So what is the same? It's the current. If we make an equivalent resistance, then that means, if we do the equivalence correctly, that means the current drawn from the source must be the same in both cases. Those two I's are the same. Okay, so let's formalize this a little bit. I'm going to get rid of this here. And let's suppose I have a bunch of resistors here connected. This is called in series. We'll define in series in a little bit. But let's say we have R1, R2 through Rn. So we have n series resistors. Not just 2, but n. And we connect these series resistors to a voltage source. Ugh, what is happening on my computer here? Okay, so I've got a voltage source. Like so. Okay, here's my voltage source. And let's say I have an equivalent resistance here, connected to the same source. Like so. Okay, so let's call this source Vs. And so this is the same source, Vs. So the equivalent resistance means that if I can find this equivalent resistance correctly, then, and if I connect that equivalent resistance, one single resistor, to the voltage source, then I draw the same current from that voltage source as I do over here. I, we'll call that I. So in both pictures here, I is the same. And in both pictures, Vs is the same. Now, we said that these are series resistors. Okay, there are these nodes here. And the definition of series is as follows. So components are in series. When they exclusively, underline exclusively there, that's the important part of this, exclusively share a node. Okay, meaning that node that they share is not shared by anything else. So these two resistors here in this picture, R1 and R2, they're in series because they exclusively share this node that I've circled in light blue. There's nothing else connected to that node. Okay, and I use the ellipses here to show that all of these n resistors are in series with one another. Okay, and those resistors, they're in series with the voltage source because there's this node here. R1 shares with Vs exclusively. So all those, this is one big series circuit. Okay, and we want to know what is the equivalent resistance here. Well, what I've got is the voltage across each resistor. We'll write that in orange. V1, V2, Vn. Okay, so each resistor has a voltage across it. Well, V, we'll call it K. So the kth resistor, the voltage across it from Ohm's law must be the current, right, through, and that current is the same for every resistor, so it does not get a subscript K, times the resistance, Rk. And from Kirchhoff's voltage law, if I sum up all of those voltage drops, from K goes from 1 to N of Vk, well, that gives me, so I sum this voltage, this voltage, this voltage, all the voltages, that must give me the voltage source, Vs. That's Kirchhoff's voltage law. Go around in a loop, right, and all the voltage must be accounted for. Okay, so now I've got K, the sum from K equals 1 to N of Vk, but Vk is I times Rk, and the I does not depend on K, so that can come out of the summation times Rk equals the voltage source, Vs. Alright, now let's sit tight on that and come over to this picture. Here I can apply Ohm's law immediately because the voltage across Req, there's only one resistor, so the voltage across it is Vs. So here I've got Vs equals I times Req. Okay? Now, if I compare, remember what we said at the beginning of this, the equivalent resistance draws the same current I when connected to the same voltage source Vs. So now let me compare these two things here. They must be equal, the Vs's in both cases, and the I's in both cases. So I've got I times Req equals I times the sum of all of those series resistors. And the I's cancel, and I get then a result that you're probably familiar with, but now you know why it is. That the equivalent resistance is simply the sum of all of those resistors. So if you go back to the original circuit that we drew, where we had the 1 kilo ohm here, and 8 kilo ohms here, those are in series because they exclusively share this node. Then, call this node A, call this node B. The equivalent resistance between nodes A and B is simply the addition, right? It's the sum. It's the sum of all of those guys. So here we have two resistors. We sum them together. That's 9 kilo ohms. That's the equivalent resistance between nodes A and B. All right, so I want to point out something. If you're not familiar with this sigma notation, this simply means it's shorthand for the equivalent resistance is R1 plus R2 plus all the way up to plus Rn. All right, well, I want to comment on this result, point out some things to you. First of all, resistances are always positive. Or we'll say you can have a short circuit, so a short circuit is zero resistance. So we'll say resistances are never they're never negative. So the equivalent resistance, Req, is at least as large as the largest series resistor. It's at least as large as the largest series resistor. So coming up to this example here, alright, we'll say that this is a variable resistor. We'll show that with an arrow going through it. So I've got two series resistors here, one of which is 8 kilo ohms. So the equivalent resistance of this thing is at least 8 kilo ohms. Doesn't even matter what R1 is, I can tell you that the equivalent resistance is at least 8 kilo ohms. Because R1 will never subtract from 8 kilo ohms, it will always add. Okay, and two, I want to point out, you should be familiar with open circuits. An open circuit is a resistor that has infinite infinite resistance. So if we had a wire in a circuit and we removed that wire, making it open, that's effectively a resistor of infinite resistance. So if one resistance is an open, then the equivalent resistance is, what do you think? So if one of these R's is infinity, then what's the sum? Infinity. It's infinity. Then the equivalent resistance is infinity. An open circuit. Okay, so in this example up here, if I had, let's say, an open circuit here, okay, there's my open circuit. One of the resistors is open. The equivalent resistance is still open. It's infinity. So the equivalent resistance now it's as if the 8 kilo ohms is not even doing anything. It's not even there, because this is the equivalent resistance, infinity. Alright, let me clear this. And I want to look at a special case. The following situation. Let's say we have resistor R1, resistor R2, and we're interested in the voltage across those guys when we have the voltage across the combination. Call that Vs. Okay, so I'll say that again. In this situation, we have resistors R1 and R2. I'll write that out, given. Given series resistors R1 and R2. And given series resistors R1, R2, and the voltage across them, Vs. The problem is to find the voltage across each one. Okay, that's the problem. First of all, let's verify that those resistors in my picture are in fact in series. So here's a node, and they exclusively share that node. So yes, R1 and R2 are in series. Okay, and so we want to find V1 and V2 in this situation. So, if there's a voltage source across that combination, then there's a current flowing, I. Okay, and we can use now our result from the previous screen, and we can say, well, if I connect a resistor R1 plus R2 to the same voltage source, Vs, then I get the same current. And now Vs is across this single resistor, so I can write an expression for that current using Ohm's law. Vs over R1 plus R2. And since this is the equivalent resistance, that current that's being drawn from that equivalent resistance is the same current up here in the original picture. That's the key. Now, I have the current that goes through both of those resistors, so now I can use Ohm's law in the original picture to find what V1 is. Okay. The voltage across a resistor is the current through the resistor, I, times the resistance. So this is I times R1. But we know what that current is. The current is Vs over R1 plus R2. Okay, and I'll just explicitly show that that's V1 again. And here is our result. A beautiful result here. Given the voltage source, Vs, and if I want the voltage across a resistor, then I use this equation, and this is called voltage division. Voltage division. And normally I'm against students memorizing equations, but you should memorize this equation because it allows you to quickly get the voltage across the resistor in a series combination. Tell me Vs, tell me the volts across the combination, and put the resistor whose voltage I want in the numerator divided by the sum of the two resistors in the denominator. That gives me the voltage across the single resistor. Okay, it's called voltage division because this thing here in parentheses, that's a fraction, okay, that's less than 1. R1 plus R2 must be less than just R1. So this is a positive fraction that is less than 1. So this thing in parentheses tells me the fraction of the total voltage that makes it across R1. And equivalently, if we looked at R2, we would have Vs, take the resistor whose voltage I want, R2, divided by the sum of the two resistors. That's going to be equal to V2, the voltage across the second resistor. Okay, that's also voltage division. And this situation occurs so frequently that we electrical engineers just memorize voltage division equations. And from this point forward, I'll just say from voltage division, and I'll just write this down. And notice here, Kirchhoff's voltage law is satisfied if we added V1 plus V2, that is Vs times R1 plus over R1 plus R2 plus Vs times R2 over R1 plus R2. The denominator is already common, Vs is common, so this becomes Vs times R1 plus R2 over R1 plus R2, and yes, V1 plus V2 equals the source. That's Kirchhoff's voltage law. If I go around in that loop, all the voltage is accounted for. Okay, so just for an example, let's say we have that 1 kilo ohm resistor here, and we have that 8 kilo ohm resistor here, and we're connecting a 9 volt source here, and I want to know what's the voltage across this resistor. Call it V1. Alright, well, I first identify that the resistors are in series. And they are, because they exclusively share that node. So, I can use voltage division because I have the voltage from here to here, which is the voltage across the combination. Okay? I've got the voltage 9 volts across the combination. So I can quickly get the voltage across 1 by using voltage division. So V1 equals 9 volts times the resistor whose voltage I want in the numerator, 1 kilo ohm, divided by 1 kilo ohm plus 8 kilo ohms. So that's 1 volt is the answer. So there's 1 volt there. You see, so that enabled me to get the voltage across that without first calculating the current. That's the quick way of getting these voltages. Now, suppose I want V2. Well, at this point I have some options, but let's use voltage division. So if I want V2, I can get it quickly. 9 volts, the voltage across the combination, times the resistor whose voltage I want, 8 kilo ohms, over 1 kilo ohm plus 8 kilo ohms. That's 8 volts. 8 volts there. And then also notice Kirchhoff's voltage law. So if I go around the loop, I drop by V1, so I drop by 1 volt. Then I drop by V2, so I drop by 8 volts. Puts me here. And then I raise by 9 volts, so that's minus 9 volts, and that must be 0. And it is. So Kirchhoff's voltage law is satisfied here. Alright, so I'm going to erase this. Pause the video if you feel the need. The next problem is the dual of what we just looked at. This is going to be current division, but also we're going to look at parallel resistors and current division. Okay, so the dual to the problem that we used when we looked at series resistors is the following. Let's say I have a current source maybe 9 amps. And you know what, actually let's keep this general. Let's not call it 9 amps, let's just call it IS. And then I have a resistor in parallel with that, and I'll define parallel in a second. And I have another resistor. I should use black. I have another resistor in parallel. And let's not stop there. Let's say we have n resistors in parallel. So let's first talk about parallel connections. It starts with the nodes again. If I identify the nodes, I have two of them. I have this one on top and this one on bottom. Always starts with the nodes. Two components are in parallel if they are connected to the same two nodes. Okay, so R1 here is connected to the top node, call that node A, and the bottom node, call that node B. R2 is also connected to A and B. In fact, all of these resistors are connected to A and B. So they're all in parallel. And they're all in parallel with the current source, which is connected to nodes A and B. So this is one big parallel circuit. So this is the dual of the previous problem. Now, we want to know the equivalent resistance. And if I take the same current, okay, same current source, IS, and connect an equivalent resistance. Are these two circuits the same? No. Nope, this one has a bunch of loops, right? This one only has one loop. This one has a bunch of components. This one only has two components. So they're not the same circuit, but what is the same here? And the same is the voltage across. So call this V, and call this V. So the voltage from A to B, okay, here's A, here's B. The voltage from A to B in this circuit is going to be the same as the voltage in this circuit. So now, really, equivalent resistances mean we have the same power in both cases. That is to say, we have the same current and we have the same voltage. So we have the same power. So if I connect the equivalent resistance to a current source, I get the same voltage. And if I connect an equivalent resistance to a voltage source, I get the same current. Okay, so in both of these pictures, IS is the same and V is the same, and we want to know an expression for the equivalent resistance. All right, well, let's look at that top picture, and we'll say each branch here, call this I1, has a current. I1, I2, all the way, all these currents, we'll call this IN. Okay, and in the top picture, the kth current, okay, in the kth branch, from Ohm's law, is that common voltage V, because V is the voltage across each resistor. It does not depend on K. It does not depend on the kth branch, because their voltages are the same. So from Ohm's law, the voltage across the resistors is V divided by the resistance, which is RK, and that gives me the current, IK. Well, from Kirchhoff's current law, the sum of all of those currents from 1 to n of IK must be the current IS. You see, because IS enters node A, and the sum of all of those currents that are leaving must be that IS. Okay? Well, we have an expression for IK that's V over RK, and the V does not depend on K, so it can come out of the summation. So we have this. Now in this picture, down here, I can directly apply Ohm's law because I have the current through this single resistor. And so the voltage, V, must be IS times R equivalent. And so IS must be V over REQ. But remember how we started this analysis. We said that the IS must be the same in both pictures, and the V must be the same in both pictures if we're going to have an equivalent resistance. So I can set these two things in orange equal to one another, and the V's drop out. And so what I get is 1 over REQ is equal to the sum from K equals 1 to N of 1 over RK. And again, if you're not used to that sigma notation, this means that 1 over the equivalent resistance is 1 over R1 plus 1 over R2 plus 1 over Rn. Okay, so it's the reciprocals that add. And finally then, the equivalent resistance then is the inverse of all of that stuff. Like so. So that's how parallel resistors combine. Okay, well let me point out something to you. First. The equivalent resistance is smaller than the smallest resistor. So compare this to our notes from the series combination. So again, this is the dual to the first property over there. The equivalent resistance is smaller than the smallest resistor. Okay, let me give you an example. Let's say we have 10 ohms here. And then in parallel, okay, well, before that, so here are nodes A and B. Okay, and we just have 10 ohms. 10 is very small. That's small. But now let's say I introduce something really large in parallel. 1 mega ohm for effect here. Mega is 10 to the 6th, a million. My claim is that the equivalent resistance between those two nodes is less than 10. Even with this thing being a million. It's true. And you can calculate it with this equation. You're going to get 9.999 something. Okay? But it is less than 10. It has to be. And let's try to understand why. Why is that? Well, let's get rid of that 1 mega ohm for right now. We'll come back to that. But let's say I connect a voltage source here and I have current flowing. And if I have current flowing, then I have electrons. I have electrons moving. Okay, and I have all these electrons and they're going through the wire and they're trying to get through that resistor. Okay, and in a resistor, they bounce into each other and they bounce off the walls of the resistor and they lose energy from heat. Okay, and that resistor could heat up. And that's actually what makes the resistance, is the resistors, or the electrons bumping into each other, bumping off the walls, and so forth. Okay, they're all struggling to get through that one resistor, and so that resistance is 10 ohms. Okay, it's designed such that that's 10 ohms. But now we put that 1 mega ohm in there. Okay, 1 mega ohm is a lot, but still, because it's in parallel, we're giving the electrons another path to go through. Okay, so some of these resistors are going to, or some of these electrons, excuse me, are going to go through the 1 mega ohm. Not a lot, because the resistance is so high. Okay, but some of them will go this path. And so, just the fact that the electrons have two paths now means that the overall resistance, the equivalent resistance, has gone down from 10 ohms because it has a second path. Alright, let me erase that. Property 2. If one of the resistors is R equals 0, okay, a resistance of 0, we call that a short circuit. Then the equivalent resistance is what? Well, let's look at this equation. If one of the r's is 0, 1 over 0 is infinity. So it doesn't matter what I add over here. I have infinity in the brackets. And then infinity to the minus 1, so the reciprocal of infinity, 1 over infinity is 0. So the equivalent resistance is Req equals 0, a short again. So again, this is the dual to property 2 that we saw with series resistors. So let's take, as an example, two nodes A and B, and there's a resistor here, maybe 10 ohms. There's a resistor here, maybe 1 kilo ohm. And then there's a short circuit. Okay, a resistor of 0 resistance. The equivalent resistance here, well, it's like the 10 ohm and the 1 kilo ohm aren't even there. The equivalent resistance is 0. No current, let's try to understand this. No current will go this way, and no current will go this way. It will all go through the short. The reason is, again, those nodes with the short, this is all one node here. This is all one node. So the difference in potential across this resistor is 0. And the difference in potential across this resistor is 0. And going back to the marble analogy, what happens when the height difference at both ends is 0? The marble does not roll, and you get no current. Okay, and then there's a third property that I want to mention here. Just kind of a quick idea, a quick calculation. If exactly 2 resistors are in parallel, let's say R1, R2, then the equivalent resistance is the product over the sum, R2 over R1 plus R2. And I'm going to use this quite a bit, and I'm not going to show the calculation when I do use it. I'll just say product over the sum. So let me just demonstrate that to you right now, why that is. We'll start with this equation, which we which we proved. So now if I have exactly 2, 1 over R1 plus 1 over R2, the reciprocal, let me get a common denominator. The common denominator is R1 times R2. So this is R1 times R2, then this has to be R2 up here, plus, and this is R1 over R1, R2. So now I can add them, R1 plus R2 over R1 times R2, and that's the reciprocal. And so when I take the inverse, that is the product over the sum. Okay, so that's a quick way of getting a parallel combination, product over the sum. We will use that quite a bit. Okay, now I'm going to erase this. Now suppose we had 2 resistors in parallel. Call this R1, call this R2, and let's say we know the current IS that approaches those parallel branches, and we want to know what's I1 and what's I2. In other words, we're interested, given these resistors and given the source current, how is that source current going to split among those 2 branches? Okay? So I'll write that down. Given IS and R1 and R2, how does IS split among the 2 branches? Okay, that is what is I1 and I2, and I do want to point out, given these 2 resistors are in parallel, they have to be in parallel for this example. So that should be given 2 parallel resistors, R1 and R2, and the current IS. How does IS split in those 2 parallel branches? Okay, well, there's a voltage from this top node to this bottom node. We'll call that V. All right? We know that 2 parallel resistors combine as the product over the sum. So we can make an equivalent picture like this. And based on what we know now about equivalent resistance, then if IS approaches that, we're going to get the same voltage. Like that. So that voltage that we get in this picture, now we can use Ohm's law directly. We have the current that goes through that single resistor. So that voltage is IS times R1, R2 over R1 plus R2. And again, that's the voltage here in the original picture. So now, if I wanted current I1, we can use Ohm's law. We have the voltage divided by the resistance. So here's the voltage now we have an expression for. That's IS times R1, R2 over R1 plus R2, and then divided by that R1. So the R1s cancel, and I see that I1 is IS times R2 over R1 plus R2. And ooh, that's a big result. That's a big result. I'm going to put a box around it. This is called current division. And similarly, if we did the analysis, I'll leave you to do it, you would find that I2 is equal to IS times R1 over R1 plus R2. Okay, that's also current division. Okay, this is the dual of voltage division. Notice here, again, what's in parentheses is a fraction. It's a positive fraction, and it's less than 1 because R1 plus R2 is going to be less than, or excuse me, is going to be more than R1. And R1 plus R2 will be more than R2. So this is a fraction, it's less than 1. And it tells us the fraction of the source current that goes through these branches. Okay, so maybe this fraction is 0.9. Well, that means 0.9 of the source current is going to go through the first branch, and then 0.1 of the source current is going to go through the second branch. Okay, it looks very similar to voltage division, but there's a key difference here, and the key difference is the subscript of that resistor and of that resistor here. You see, if I want the current through the first branch, I1, then I put the resistor of the second branch up there. If I want the current in the second branch, I put the resistor of the first branch up there. Okay, let's take a concrete example. Let's say I have 9 amps. And I have a 1 kilo ohm resistor here, and an 8 kilo ohm resistor here. And I want to know quickly, what is the current in this branch, and what is the current in this branch? How does the 9 amps divide from those two branches? Well, I can get this quickly using current division, and I ask that you memorize this, and I will just simply write this down from this point forward. I1 is the source current, 9 amps, times the branch or the resistance that we don't want, right? 8 kilo ohms divided by 1 kilo ohms plus 8 kilo ohms. So that's 8 amps. And I2 is 9 amps times the resistance of the other branch, 1 kilo ohm over 1 kilo ohm plus 8 kilo ohms. That is 1 amp. Notice that they add to 9. They have to, because Kirchhoff's current law must be satisfied. Here's a node. We've got 9 amps going in, and we've got I1 and I2 leaving, so they must add to 9 amps. And also, this branch, notice, has more current than this branch, and that's because its resistance is less. So less resistance draws more current. In fact, this branch has 8 times the resistance of this branch, and so its current is 1/8 of this guy. Lots of nice things that we're seeing here. Now, resistors don't have to be in series or parallel. They can be neither. Let me just give you a quick example of that. Say I have a voltage source here, and a resistor here, and a resistor here, and maybe another voltage source there. Call this V2, this is V1. R1, R2, and R3. So these guys are not in series. R1 is not in series with R3. let's look at the nodes. Here's a node, right? Here's a node. Here's a node. Here's a node. And here's a node. So we can reference them. Let's call this A, B, C, and D. So R1 is connected to A and B, right? R2 is connected to B and C. B and D. R3 is connected to B and C. First of all, neither one of these resistors is connected to the same two nodes, right? So none of them are in parallel. None of them are in parallel. You might think R1 is in series with R3 because they share this node B, but R2 also shares node B. So remember that exclusively, you have to share the node exclusively to be in series. So R1 is not in series with R3. So that you cannot combine any resistors here. All right? And I want to point out that this thing, let me use a different color, this resistive network, okay, that is a terminal means a node, 3-terminal network, resistive network. There are transformations you can do, equivalent transformations you can do for 3-terminal resistive networks. And this is the so-called delta Y transformation. So I'm going to erase this. And that was just simply to motivate our final topic of discussion here, and that is the delta Y transformation. Now, I spent some time and I proved how series resistors combine, and I proved how parallel resistors combine. I'm not going to prove this one. We're running short on time, so I'm just going to explain it a little bit, give you the result, and direct you to your textbook if you are interested further, or if you want to see the proof. So we'll call this node 1 here, node 2 here, node 3, and node 4. And let's call these resistors, we'll call this one RA, and RB, and RC. Okay, this is a 3-terminal network, because nodes 2 and 4 are actually the same node, right? But between 1 and 2, they have a resistor there. So 1 is not the same as 2. 1 is not the same as 3. There's a resistor between them. And 3 is not the same as 4. There's a resistor between them. But 2 and 3 are actually the same node. This is a delta configuration. The Greek, capital Greek letter delta looks like this. So this is delta. That's the delta configuration. And it can be transformed to a different configuration that looks like this. We'll call this R. We'll call this R. The book uses R1. Call this R1. Yeah, your book uses R1 there, and R3 here, and R2 here. All right, and this is also, we'll call this A, call this C, call this B. This is a 3-terminal network as well. And this is the Y configuration. So you can imagine if I didn't draw R1, R2, R3 at right angles here, I could have drawn them like this, equivalently. Okay, so this is the Y configuration. And there's an equivalent transformation to get from this picture to this picture, or from this picture to this picture. And that equivalent transformation is as follows. And again, I'm not going to prove this. Your book does a nice job of it. But the resistor R1, so this resistor over here, is equal to RB times RC over RA plus RB plus RC. So if you had this picture, the delta picture, so you would have RB, RA, and RC, then you can get R1 with this equation. And similarly, R2, if you notice what's not in the numerator here is RA, right? So that was what was connecting here. So R2 is B, so RB is going to be missing in the numerator here. RA plus RB plus RC. And then finally R3 is equal to, let's see, we left off A, then we left off B, so now we leave off C in the numerator. Okay, and these are our equations to get from delta to y. And so just to motivate why you would do this, let's say you have a resistor here, call it Rx. And then you have this picture, Rc, Rb. This is a common picture for high power systems. Alright, so let's say you have this picture, and if you transform it now, this is the delta picture. If you transform this into a y, then you would have this picture. Right? And now what do you notice about Rx and R1? Rx and R1 now are in series. So now you can combine R1 with Rx into one resistor, and then you can transform it back to delta if you want, thereby eliminating one of the resistors. So you've simplified the picture. So that's if you had a delta picture and you wanted a y picture, here are your equations for those guys. Now, you can go back, if you have the y picture, to the delta picture with the following. Ra is R1 times R2 plus R2 times R3 plus R1 times R3 over R1. And similarly, RB equals, and you've got all those combinations again, R1, R2 plus R2, R3 plus R1, R3 divided by R2. And finally, RC is R1, R2 plus R2, R3 plus R1, R3 divided by R3. So these equations apply if you are currently in the Y configuration and you want the delta configuration. These guys give you the transformation back to this picture.